kind of understanding that we usually use, that, oh, like running time, it's not even just memory, it's really like hierarchies, and these things make a real difference. That's why like certain things work, certain things don't work. So from those perspectives, it could be that something like that does work if you exploit memory the right way. And I think like in practice with some of these techniques around speeding up transformers, I think they try to do something like that with some approximations to attention. But I don't think it's as rigorous. And the difficulty in making it rigorous is also to first come up with the right model for what is efficient and what is not, which I think would be really helpful for the field. Yeah.
That's sort of preconditioning.
Yeah, that's a good question. So if you had the right preconditioner, then you could do, like, you could correct for like this bad curvature. And I think like many techniques try to do that. I think if we look at in terms of like what is possible, I think in general you cannot find this preconditioner without using quadratic memory itself. So in general, like as far as I can see, in order to even find this right preconditioner, like it would be a D by D matrix, and it doesn't seem like you can do that without also using quadratic memory. But like in practice, like preconditioning does help in certain settings, but not as much, to be honest. Like we don't really use preconditioning that much in practice and like optimization for like deep learning. Yeah. Shampoo and stuff. Yeah. So those are like, they're kind of trying to like get some second order information without using the full second order information. So instead of like keeping around the full Hessian, you kind of approximate the Hessian like for like certain matrices and so on. And that does give certain benefits. I think there seem to be at least some speed ups, like by some constant factors in certain settings at least.
Is there a place where you can exploit this low rank structure there to actually build the work?
I think it's possible. Yeah, I think it could be that for certain like low rank structure, one actually shows a faster rate. So yeah, I can say, for example, even for things like this shampoo and soap and so on, like we don't know of settings where they are actually provably faster, which is kind of weird. So maybe like something like a low rank setting, like something where there is a low rank structure in the Hessian, they could be provably faster. That could be interesting. I think maybe that could be something where there is something in between. Or you can at least get these faster rates without using as much memory. Yeah, Ashwin?
So the question is similar flavor. On the next slide, you said you can get for the first order method, you can improve depending on the condition number.
For certain structured settings again. So sorry.
That should not be possible in general, right? Like that.
Not in general, yeah. This is really for some structured linear systems.
Somehow, like value that we gave a certain.
Exactly. So like what we need is a small number of distinct eigenvalues. So the eigenvalues have to be clustered.
So now the question is condition number somehow the right axis to consider? Like what is there some notion of an effective condition number that we should instead?
That could be the case. I think in general, I still think that like if you don't have this structure in your eigenvalues, for example, then just like if you look at the condition number itself, I don't think you can get around like this polynomial dependence in condition number in terms of convergence rate. But I think it could be that there are better metrics in condition number. In some sense, that's what this work tried to do. Like basically argue that what you need is like if each of your individual, if you have a small number of eigenvalues and each of these eigenvalues or within each of these intervals themselves you're well conditioned, then that could be fine. So there could be more nuanced things than condition number which capture complexity of gradient descent. So that's exactly what the point of this work is really. Okay, I think I'm out of time. So tomorrow maybe I'll talk about how we can use some of these perspectives in optimization theory more generally to try to understand how transformers solve linear regression in an online setting. So we can talk about that tomorrow. Thanks so much. Take any questions.
Your time for questions.
Yeah.
It's a kind of silly question. There was a work of Garnet Paris where he looked at this kind of small step, large step.
Yeah.
For this low rank problem where the rank is not exactly known.
Sorry, what is known?
So it's called low rank problem where the rank is not exactly
known. Okay.
Is there any connection on that with this?
Yeah, I think there is. Yeah, I've seen that. I think that is also using some sequence of large and small sizes. And I think there's been some other interesting work on that too. So there's this work on the silver step size schedule, which is also like really cool. It gets a faster convergence rate than 1 over epsilon squared than what we know for just one Lipschitz convex optimization, using some sequence of like these step sizes, which also look kind of like this large and small step sizes. So again, there you can get these faster convergence rates. So in general, it does seem like there is power in choosing some right step size sequence, and that could even lead to provable benefits in terms of your convergence rate. I think like if you look at like in terms of practice, I guess people do use like a variable learning rate schedule, but it's usually not as principled or as structured. So I think there's still quite a lot to go from like these kinds of ideas to actually better choice of learning rates and optimization in practice.
Just for any general, better than 1 over epsilon.
Yes, that is for a general setting. Yeah.
All right. This is the time.
Sir. Oh, sure. Okay, so it's now time to introduce our lecture awardee for this year, which is Ashwin Pananjady, who is a assistant professor at Georgia Tech. So Ashwin and TIF are known to each other. So he came as an intern here 10 or 11 years ago with Vivek, his fellow intern, and spent some, I think, couple of months braving rains. And what he has to write is he has fond memories of trying to prove theorems in TIFR, negotiating monsoon rains in Colaba, and competing for standing room on the Virar fast. I think his challenges were slightly more than that. He also had to stay in Colaba in one room shared with somebody, and lots of interesting things happened over there. So he got used to Mumbai life, and I think decided never to return here because of that. So he has too many long list of awards he has already won, so I'm not going to list all of them. Some of the ones we know are the President's Gold Medal from IIT Madras. Once he graduated from IIT Madras, he went to Berkeley, did a fantastic PhD, had too many job offers, chose one, and now he's, I think, already close to tenure or pre-tenure.
It's not jinx it.
Okay, so yeah, so he's doing some wonderful things, and I had something else to say. All right, so it's time that we listen from him what he is up to for the past few years. So over to you.
All right. Can everyone hear me in the back? Just to set the record straight, it was the governor's gold medal. The president's is for really smart people. The governor's is for less smart people. Like yeah. Anyway, so thank you very much for the invitation. I really appreciate it. I really appreciate the award as well. Thank you for everyone who was involved in that. And hopefully today I won't bore you very much. So here's the plan. This talk is, of course, in two parts. And I've titled this series of lectures, Predicting the Behavior of Iterative Optimization with Random Data. So there are two keywords here, predicting and random data. So in some sense, it's an average case analysis talk. Today, I'm going to really be telling you about sort of the conceptual takeaways from what something like this can tell you. And then tomorrow, I'll jump into more technical details. This is not to say today's talk will not be technical. It will be. So I'm warning you in advance. But it's not going to be as technical as tomorrow. So that's also a warning in advance.